Just wait for 2 3 minutes. After that, it's okay. Let me start. So this is the fourth week, problems of discussion. So today's plan is first we will discuss the assignment questions, week 3 assignment questions, and then we will do couple of scale analysis based problems. These are, I would not say these are problems, but these are just the equations which we have so far learned. In those equations, we will apply this mid-latitude based synoptic systems based scale analysis and see that how those equations, which are complicated, how we can reduce it to a simpler form based on the mid-latitude synoptic weather system. Okay, so this is one of the, I would say, regional assumption which we take. Uh, so we will see those things. We will apply and we will derive certain factors. Those factors will be helpful for your this week 4 assignment questions. I was going through the assignments of week 4, so I saw that couple of questions which might not be covered. So those things we will try to discuss a little bit. Okay, and finally, we will go to the week 4 content where the waves are being introduced. The atmospheric waves. So we'll go to the basic physics of those atmospheric waves and We'll try to see that why we need to study the atmospheric waves, the wave theory, the atmospheric wave theory. Why do we need to study it, and how do we proceed for this kind of a, this wave theory? Okay, so these are the couple of plans which we have today. And so to begin with, we will start with the assignment questions. I would not say that in the assignment 3 there are problems. There are simple one-liner MCQ questions, what I have seen so far. So let's see. Open up. So this is the week 3 assignment. Okay. The first question is that in which layer do virtually all the weather phenomena takes place? So there are a couple of layers. So those who have uh, the idea of atmospheric physics, they they know about these layers. And number two is that uh, those who have also done the course, the introduction to, I think, atmospheric and space sciences of NPTEL, they have learned this kind of a thing. So I will just briefly describe what are these layers. And so the answer is the troposphere. And let me just go here. And so we generally, this is a very basic thing. We generally see the how the temperature profile looks like when you go to the top of the atmosphere. Okay. So this is your height, okay, in Z, the height coordinate, and this will be the temperature. Okay, and we differentiate or we divide the temperature profiles into a couple of layers. So the bottommost layer is, we call this layer as the troposphere. Okay. This is the bottommost layer. What happens here is that, so you have this is your surface. Okay, because Z is equal to 0 is your surface. Correct? Z is equal to 0 is your surface layer. So in the surface layer, when the solar radiation falls, the surface temperature, based on the surface properties, of course, the surface properties, some it will reflect, some radiation it will reflect, some it will absorb, and some it will scatter. But yeah, surface cannot scatter, so it will reflect or absorb, right? So but remember, this surface of the earth is a poor conductor of heat, so it will not penetrate much. The heat will not penetrate much. Okay, so because of that, the temperature is very high near the surface. But as you go to the top of the atmosphere, you see that the temperature decreases like this. It might not be so much linearly, but yes, almost it is a in a linear fashion. It decreases with height. Remember, with height. With see, we can make this raise to pressure coordinate also. So that is another complication. So we will not go into detail of that. So this is how the temperature decreases, linearly decreases, and the rate at which this temperature decreases, we have I think discussed in last to last session. This dTdz is called generally the lapse rate. Okay. Sometimes it is called as the temperature lapse rate. So it is the rate of, you can keep a minus sign also, the rate of decrement of temperature with height is the lapse rate. Okay. So this is your temperature decrease with height. Okay. After that, there is a equilibrium layer which is called, very small layer, which is called the tropopause. So I will make that. After that, what happens is that the stratosphere starts, and in the stratosphere, your temperature keeps on increasing. Okay, so this increases. Again, there is a layer which is the stratosphere. After stratosphere, there is a pause, and then there is again a decrease, and this decrease is huge. Okay, it reaches almost up to minus 90 degrees. Okay, so this decrease is almost up to minus 90 degrees Celsius, which is very, very cold. Okay, and again there is some pause, and then there is a increase. Okay, so let me just clean this one up and also clean this one so that the figure is properly visible. So this is what it is. You can make the axis like this. Okay, so yeah, and it goes on. Okay, so this this layer is the thermosphere. Okay, after that exosphere starts, the atmosphere's last part. Okay, after this, but there the temperature is very large, essentially very large. Okay, so it keeps on increasing. The most important thing is that if there is so high temperature, okay, so but the problem is that here the density of means the particles are very less. Most of the particles are concentrated near the lower atmospheres. Okay, so thing to remember is that this is thermosphere. This pause layer, which is here, this pause is called the mesopause. And this layer, where the temperature follows the similar pattern of that of the troposphere, is called the mesosphere. And the important factor of this mesosphere is that it is that layer where the temperature is almost minimum, minus 90, minimum observed over the atmosphere, anywhere in the atmosphere. Okay, so this is the mesosphere. This pause is called the stratopause. As you can see, the next layer is the stratosphere. So this is the stratopause. And this layer, where the temperature just after the tropopause increases, is the stratosphere. Okay. And finally, this pause is, you can guess what it is. It is the tropopause. It also, this tropopause height generally changes from equator to the poles. Over the equator, because of strong updraft, because of strong wind convergence, there is a uh, there is the tropopause height becomes very strong, okay, or large, I would say. But near the poles, it is weaker. It comes to a lower level, like about 12 kilometers or so. Okay, so this is the tropopause and this layer is the troposphere. So all weather events which we see occurs in the troposphere. Okay, because of the heating, of course, because of the heating and the wind-driven circulations. The wind-driven circulations also occurs in the stratosphere, but it is very weak. Okay, so all major weather events, whatever we see, cyclones, then you tornadoes we don't see in India. So cyclones and whatever you see, monsoons, whatever. So monsoons are also not a weather event. It's a seasonal thing. Okay, day-to-day weather events like cold winds, okay, heat waves, cold waves, all these things, all these events generally we see are or the thunderstorms. So all these weather happens at the or occurs at the troposphere, the lowermost layer of the atmosphere. Okay, so this gives you a complete structure of the temperature profile of the atmosphere. So I will write it like this. It's a temperature profile, or temperature, you can say vertical profile of atmosphere. It's a big, this is the basic. Now you can solve many other questions based on this. Okay, fine. So as I have mentioned that the lowermost layer, which is generally, I would say, very unstable, that is your that is where you find most of the weather events. Okay, so that is important. And why do we see that? A very common reason is that See, the temperature decreases. So wherever the temperature is low, your density becomes very high. And wherever temperature is high, your density becomes very low. Based on the ideal yes law. Right? P is equal to rho RT. So if you fix the P for the time being, so you can see that rho is somewhat inversely proportional to temperature. So wherever temperature is low, suppose here you find that your density is more, your density is low. So this becomes an unstable layer. So why? Because if you put high dense material over low dense material, so what will happen? It will try to come back. And this process leads to majority of the weather events. Okay, because there is a vertical transfer of dense medium, not the dense air. Okay, so this creates majority of the weather events. Now you can ask that why in the mesosphere here also temperature decreases and the lowest temperature we find. This is because the number of air parcels or the particles which are present over these mesosphere, the mean density of the mesosphere is very, very less compared to the troposphere. As you can understand, most of the dense air or the dense, I would say, particles of the atmosphere are in the lower side, in the lower levels. Okay, so that's why in the mesosphere we don't find, but yeah, the structure is quite close to the convective structure. Okay, so these are the couple of things we must know. Okay, so let's go to the questions now. Yeah, so in which layer do virtually all weather phenomena? Yeah, yes. Hmm. Hmm. Tornadoes. हाँ, राइट राइट यूएस में दिखाई देता है कुछ कुछ जगह पे हाँ वो हाई लैटिट्यूड्स में दिखाई देता है हाँ ये ठीक है दिस इज राइट इंडिया में नहीं दिखाई देता है ये वो पर्टिकुलर वेदर इवेंट है उसी जगह के लिए यू आर राइट बट दिखाई देगा मैं जो बोल रहा हूँ कि द लोअर मोस्ट लेयर ट्रोपोपॉल ट्रोपोस्फियर वहां पे ही दिखाई देगा उससे ऊपर नहीं जाएगा मैक्सिमम बिकॉज उसके ऊपर जो स्ट्रेटोस्फियर है इट्स मोस्टली स्टेबल लेयर जो मैं डेंसिटी वाला एक्सप्लेनेशन दे रहा था हाँ, okay so yeah okay so the first question the answer is troposphere weather phenomenon occurs at the troposphere be it tornado be it cyclone be it anything. Right. The second one is the largest wind patterns are seen at. So now questions are on the scale, different scales. Okay. So you have different scales, mesoscale, synoptic scale, planetary scale, and microscale. We have discussed last time. So generally, largest wind patterns are seen in the planetary scale. So why? Let's see this. So for the second, so there are different scales. Okay, largest wind patterns are on the earth are nothing but the jet streams. Okay, jet stream. So you will see. Let me show you a graph that will be helpful to understand. Mm, let me see. Mm, wind easier to visualize. So that's why I try to change winds. So look at this. Seeing the largest altitude. So see this 500 hectopascals I have chosen, that is about 5,500 meters or about 5 kilometers from the surface. You can see here 5,500 meters it is written. Okay. So I have chosen 5 kilometers from the surface, a level. Look at the winds. See the large scale wind patterns in the magenta color or the violet color, whatever you say. See, there is a large scale pattern, and you can see it much more as you go more to the north. See, it's a huge scale pattern. These are generally called the jet streams. Okay, there is a subtropical jet which is found here in this part, as you can see, and there is another one which is called the polar jet. Okay, so these are the jet streams. Jet streams is a large volume of winds meandering and moving, circumferring the Earth, covering the entire Earth. Okay, so these are the jet streams. See, these are planetary scale. All over the planet, you will find this. You see, right? So these are called the jet streams, which are generally temperature driven between your this area and the area above. Okay, so you can see there is a it's the entire world. It is covering the entire world, right? So that's why these are called the planetary scale. Uh, or this, if you just talk about um, the length scale, it is the planetary scale. Entire planet it is covering. Okay, so these jets generally cover entire planet, and this generally will be more stronger in the south. See, because in the south it is right now winter, so these are much stronger, and you find it over the entire Earth. Okay, so this website you can visit, this windy website. So many weather phenomena you can see not only over the world but over Indian region as well. Okay, this is 500, so you can go, you can choose your altitude. So you can go to say 850 or 900, which is 3,000 feet or 900 meters. You see there is a very strong wind pattern which is present here, but it is the monsoonal winds. It's not the global scale pattern. Okay, one must visit this website windy.com. Yes, you can, uh, in case you get free time, you should watch it. Okay, let's go to the question. So, as I have shown you, these are the planetary space system. See, now I will just write. I think I have shown it in the last uh, problem solving session. So, mesoscale are generally in some kilometers, like 10 to 1000 kilometers. Okay, if you go to the spatial scale, mesoscale is about 10 to 1000 kilometers. Synoptic scale is around 1000 to 2500, 3000 kilometers. Planetary scale is huge, entire planet, about 5000 kilometers. And microscale is very small, about 1 kilometer, less than 1 kilometer even. Okay, so the planetary scale will be perfect for largest wind patterns. And these largest wind patterns are what I have shown. Okay, so jet streams are the largest wind patterns that circumfere the Earth, right? So these are planetary scale covering the entire Earth. That's why its average length scale is 5000 kilometers. But if you look at the synoptic scale, which are like cyclones, okay, cyclone, then your hurricanes, these are all same thing. Hurricanes, western disturbances, which happens in the northern India during winter. Okay, western disturbances. These are all synoptic scale, which is about 1000 to 3000 kilometers. Okay. Next is mesoscale. Mesoscale is like thunderstorms. Then there is another event called the nor'westers. Nor'westers, particularly those who are from the eastern parts of the India, they face it more. The northeast, east, this portion, just before the onset of the monsoon, just before the monsoon, like April and May, typical means there is a series of thunderstorms forms. So those are called the nor'westers, called the Kalwesters. Okay, so this is another event. This is the mesoscale event that is up from 10 kilometers to 1,000 kilometers. So yeah, and microscale is very very small, AD type, which is roughly much less than 1 kilometer even. Okay, so these are couple of things one must keep in mind. Okay, let's go to the third question. Which of the following atmospheric layer has temperature profile that promotes convection? So we have already seen the temperature profile that promotes convection is that the temperature decreasing with time. So, what are the options here? Mesosphere, stratosphere, thermosphere, and exosphere. Exosphere is the last part of the planet, so don't need to worry about it. Thermosphere is very high, temperature increases. Stratosphere it increases, but mesosphere is the only place where the temperature decreases. But it will not promote convection there for sure because there is no moisture. Because moisture availability happens only near the surface in the troposphere or that too lower troposphere. Okay, so mesosphere is the correct option, but I would say that this question is incorrect because it will never promote convection. But yes, the temperature profile is similar to the troposphere, which promotes convection. Okay, so mesosphere is the correct option. Fine. Let's go to the fourth one. In a mid-latitude synoptic system, which of the following have the largest unit scale? So we have this down in the last time. So couple of things are written: horizontal velocity scale, vertical velocity scale, length scale, time scale. So length scale is the correct option. So just list down it. This is the fourth item. So U, that is the horizontal wind vector, has in the mid latitude synoptic scale, it is about 10 meter per second. The length scale, horizontal length scale, is 10 to the power 6 meters. Okay. The vertical velocity is 10 to the power minus 2 meter per second. And what else is given there? Time scale. Okay. So the time scale T is nothing but U by L, right? So meter per second and by meter, so it will be uh, no L by L. So it will be 10 to the power 6 divided by 10, which gives you 10 to the power 5 seconds. Okay. So out of which L, the horizontal length scale, is the maximum. Fine. This is done. Okay, come back. Fifth one is that in the mid-latitude synoptic system, which of the following force or forces are mainly responsible for horizontal atmospheric dynamics? Well, the major force, I would say, is the pressure gradient force, but in certain cases, centrifugal forces can also act. So, here the option D, both B and C, must be correct. So, it's not incorrect, but based on the question, I would rather say the pressure gradient force is the major force. Centrifugal force value is very, very small. So the pressure gradient force is the major force. So instead of giving both B and C, which is partially correct, I would say, but C is the correct option, the pressure gradient force. Okay. In mid-latitude synoptic system, which of the following forces are responsible for vertical atmospheric dynamics? So here gravity is number one, which is very important, and pressure gradient force also. Why? Because sixth one, because if you look at the momentum equation, dw dt is minus 1 by rho delta p delta z minus g, and there is a Coriolis force also. But Coriolis force magnitude is very very weak there. I will show this. I will show this through what you call your scale analysis, that you will find that this Coriolis force is very very weak. Okay, this the previous one, the fifth one, can also be shown. Okay, so this I'm not showing, but the sixth one I will show using scale analysis today. That you will see that the Coriolis force is very very weak there. Okay, so this is one of the things. So it's pressure gradient and gravitation, both B and C. In the scaling analysis of continuity equation, compressibility is considered in which kind of motions? So it will be in the vertical motion. We will see today. I have not covered this. Okay, which of the following atmospheric system has the largest length scale? See, hurricane and cyclone both are same, but the names are different at different areas. Okay, so I don't know that why the accepted answer is only cyclone, but cyclone and hurricane shares the same playing scale. So I am not very sure about this. I would say if you go ahead with cyclone, that is also correct. Hurricane is also correct. I'm not very sure about this, but why particularly cyclone is mentioned in as the answer. Okay, so let's look for other things now. Scale analysis, particularly, we will apply and try to see a couple of things. Okay, just give me a second. Okay, so today we'll start with some scale analysis part, and then we'll last we'll move towards the waves. Okay, so scale analysis. We have seen different values of the mid latitude synoptic. So this will be particularly based on mid latitude synoptic systems. Synoptic scale I have already shown. Synoptic systems. Okay, where length scale is about 10 to the power 6 meter, h is 10 to the power 4 meter, the vertical height, then u is 10 meter per second, and u and v are same, and your w is 10 to the power minus 2 meter per second, and what else? F is 10 to the power minus 4 per second, omega is 7.29 into 10 to the power minus 5 radians per second. Okay, what else? What else? Yeah, that is fine, I think. Oh, G is 10 meter per second square. We know this value is known. Almost 10. It's not actual 10, but we'll make it similar to 10. Okay, let's see. Okay, uh, delta P by rho is 10 to the power 3. Okay, so it is pascals per kg per meter cube, 10 to the power 3. This is, and delta P horizontal scale is 10 hectopascals, which is roughly of the order of 1000 pascals. And delta P, so this is for the horizontal, it's Y. But delta P for Z, that is vertically, if you vary the pressure, it is about 1000 hectopascals, which is of the order 10 to the power 5. We know this is the one atmospheric pressure. Okay, so these are the couple of things which we have discussed so far, and we will apply it. So in the last session, I was applying the horizontal momentum equation. We will start from that. Okay, so let's do that. Okay. So first we will try it with horizontal momentum equation. So let's do it. Horizontal momentum equation. All right. So what is the horizontal momentum equation? So it's delta u delta t. Write the entire term delta u delta t, u delta x. So this is the local, this is the adjective term, v delta u delta y plus w delta u delta z is equal to minus 1 by rho delta p delta x and plus f v. Right? This is your horizontal momentum equation. Just a minute. So this is your horizontal momentum equation, and we will apply the scale analysis on that. Okay. What is the first term? Delta U, delta T. So delta U, that is the horizontal velocity of the zonal velocity. So you can put the scale of that as U. Okay, divided by, this is the time. So put it time. Okay, I have forgot. T is 10 to the power 5 seconds. Okay, so U and U by T plus. This is what U. So I'll keep it U. Delta U, delta X. So delta U's dimension will be U, and X is the length scale in the horizontal direction. So it is L plus V, U and V are same for the scale analysis. This is also U divided by L plus W. W is W. Let us write it W. This is U, and Z, delta Z is the height. So H. This is equal to my, don't put equal to A, minus 1 by rho and delta P. So can you write it like delta P by rho, and delta X is L, and this is F plus F into U. So this is the scaled part. Okay, this is the scaled part. Okay, so now this T, time, can it be written as L by U? So you can write it like that. So it will be again, this part becomes what? U square by L. So you can see for everything it is U square by L. This is also U square by L. This is also U square by L. But this is U times W by H. What is this? Delta P by rho L and FU. FU. Sorry. Okay, so what is U square by L? It is 10 meter per second square divided by 10 to the power 6. Same here, 10 square by 10 to the power 6. This is 10 square by 10 to the power 6. This is 10 into 10 to the power minus 2 divided by 10 to the power 4. Delta P by rho. So anywhere you do, rho is generally 1 kg per meter cube. Okay, this is thing to remember. So delta P, this is in the horizontal scale, x, right? So this becomes 10 cube Pascal divided by L. L is 10 to the power 6. What is F? 10 to the power minus 4 into 10. Correct? So these are the scaled values of the horizontal momentum equation. Remember, in the mid-latitude synoptic system. In the tropics, it may be different. Fine. Let's go ahead. This is 10 to the power minus 4, 10 to the power minus 4, 10 to the power minus 4. And what else? This is 10 to the power minus 5, right? 10 to the minus 1, yeah, 10 to the power minus 5. What about this? 10 to the power minus 3. And what about this? 10 to the power minus. So what do you see? Entire term of the LHS, these are the RH. So entire term of the LHS is either 10 to the power minus 4 or 10 to the power minus 5. But look at the RHS. So this is the RHS, this is the LHS. In the RHS, all terms having scale value 10 to the power minus 3. Therefore, the 10 to the power minus 3, which one is larger? 10 to the power minus 3 is greater than 10 to the power minus 4 or 10 to the power minus 5. Correct? So if this is greater, that means these two terms must be dominant. This must be dominant. So in the right hand side, what are the terms there in the original equation? This. The horizontal or the zonal pressure gradient force and the Coriolis force, the horizontal Coriolis force. So these two terms are dominant. Okay. So dominant terms based on the scale analysis for the horizontal momentum equations are the pressure gradient term minus 1 by rho delta P delta X plus the Coriolis term, the horizontal Coriolis force term. So this is equal to 0. This is your dominant balance. Once you have applied scale analysis, you can see that this is the final dominant balance because all other terms are one order of magnitude smaller than these two terms, right? So this is my final equation. But remember, in this equation, there is no time curve. That means you cannot predict in time what will be the change in the particular field, like pressure or U or V, nothing. This is we call as diagnostic balance. diagnostic. You cannot predict, can't be predicted. Just a balance. Okay. But in the original equation, you are having this, the prognostic term. This is called the prognostic. Prognostic. That is, you can predict. How you can predict? Just by integrating, right? The delta t, if you just do integrate. So this can't be predicted, but it's a very important balance. Okay. So let's see what is the value of v from this. So v will be equal to 1 by rho delta p delta x and the sp. This is what generally or famously termed as the geostrophic balance. This is the geostrophic balance, where pressure, gradient force balances the Coriolis force, and any other inertial forces are absent. So this is called the geostrophic balance. Okay, so when you do, if you do the same thing for the meridional momentum equation, that is involving the v, that will also give you the similar kind of a balance. So for the from the meridional, from y momentum equation, from y momentum equation, you can get u as minus 1 by rho f delta p delta y. Okay, this minus will come automatically. You will see in the Coriolis sign, you will get it. Okay, so these are the geostrophic balance. Both are geostrophic. Okay, so this is another important thing. Here we define a field called the Rossby number. Very important field, Rossby number, denoted as R naught, which is inertial force to that of Coriolis force. It's a ratio of the inertial force to that of Coriolis force. How it is defined? It is du dt, the inertial part du dt divided by the Coriolis part, which is f times v. Okay, or yeah, f times v. Fine. So how will you do that? Okay, if you have to do a scale analysis of this, how will you write? See, du is there, so you can write u and dt. So actually, it's this is the scale part. Okay, if you just follow everything, you'll get the u by fl. Okay, fine. Let's forget about the scale part. Let's see how this R naught is related to this. Okay, so what is my momentum equation? Original. So original momentum equation was du dt, which we have written as this delta u delta t plus the advection term. So du dt is equal to minus 1 by rho delta p delta x plus fv, right? So what is the definition? Du dt. Let me divide it by fv, the Coriolis part. So what I will get? Minus 1 by rho f v delta p delta x plus fv by fv, which is 1. So what you get? This, the left hand side is your Rossby number, R naught, which is equal to minus 1 by rho f v delta p delta x plus 1. Now, can we say that if your R naught tends to 0, if I make some way this R naught, this Rossby number tends to 0, what will happen? It will be 1 by rho f v delta p delta x will be equal to 1. Can we write this from this? Yes. Finally, can we write v is equal to 1 by rho f delta p delta x? What is this? The geostrophic. Same. So this is the geostrophic balance. So one thing to remember is that if your Rossby number tends to 0, becomes very, very small, then the horizontal momentum equation becomes A geostrophic balance. Okay, just remember this. This is important. Okay, fine. This is one of the important stuffs uh, which will be helpful. Okay, so I have shown the horizontal momentum equation scale analysis. Let's see the vertical momentum scale analysis. Okay, so let's do. Yes, yes. Hmm. एक यूज तो ये है कि रॉसबी नंबर जो है वो अगर छोटा है दैट मीन्स ये एक हम प्रोग्नोस्टिक इक्वेशन से एक डायग्नोस्टिक बैलेंस में लेके आ सकते हैं जैसे जो अभी मैंने एक सर्कुलेशन दिखाया था याद है मॉनसून का सर्कुलेशन हाँ हाँ विंडी वाला तो उस सर्कुलेशन में तो दिखाई देगा कि एक मिनट में दिखाई ही देता हूँ हाँ, ये जो जगह है देखो इसके जस्ट ऊपर ये जो विंड्स इधर जा रही है फ्रॉम वेस्ट टू ईस्ट इसके जस्ट नॉर्थ में प्रेशर बहुत कम होता है लो प्रेशर होता है बट उसके नीचे क्योंकि ओशियंस जो है ठंडा है टुवर्ड्स द इक्वेटर साउथ इंडियन ओशन वो जगह पे प्रेशर ज्यादा होता है तो वो जो प्रेशर ग्रेडियंट हुआ उसके वजह से और अर्थ का जो रोटेशन हुआ है क्योंकि वो इक्वेटर से काफी दूर है ये जगह तो कोरियोलिस फोर्स और प्रेशर ग्रेडियंट का एक बैलेंस तैयार हुआ और उसके वजह से ये विंड्स होना शुरू हुआ तो ये जगह मैं बोल सकता हूँ ये जो अरबियन सी रीजियन है बे ऑफ बंगाल रीजियन है जहां पे टर्निंग नहीं हुआ उतना तक वो रीजियन में मेरा रॉसबी नंबर जो है वो बहुत स्मॉल होगा तो ये एक्चुअली स्केल फैक्टर है मैं बोलूंगा इसका एप्लीकेशन वैसे ही हम लोग यूज करते हैं कि जहां जहां पे हाँ हाँ ओके हाँ 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 साउथ अफ्रीका के नीचे हाँ होगा क्योंकि जितना तुम मिड लैटिट्यूड की तरफ जाओगे वहां पे ये चीज हर बार अप्लाई होगा क्योंकि वहां पे मेजोरिटी जियोस्ट्रॉफिक बैलेंस होगा और एक्चुअली जियोस्ट्रॉफिक तो कंप्लीटली नहीं होगा क्योंकि कर्वेचर है देखो जो भी विंड का पैटर्न है उसमें कर्वेचर है उसमें ग्रेडियंट विंड बैलेंस यूज होगा सेंट्रीफ्यूगल भी अप्लाई होगा वहां पे तो ये कंप्लीट जियोस्ट्रॉफिक तो नहीं होगा बट अप्लाई तो होगा डेफिनेटली अप्लाई होगा क्योंकि ये आर नॉट डिफाइन किया जा रहा है किससे मिड लैटिट्यूड सिनॉप्टिक्स से तो मिड लैटिट्यूड एक्चुअली ये है बस तो ये एप्लीकेशन है डेफिनेटली यहाँ पे होगा और हम अपने विंटर के टाइम पे हमारे इंडियन रीजन के नॉर्थ में होगा इस रीजन पे ये जो न्यू दिल्ली इस region, यहाँ पे अप्लाई कर सकते हैं ठीक है हाँ तो ये एक है ओके लेट्स गो टू द सेकंड थिंग व्हिच इज द वर्टिकल मोमेंटम इक्वेशन तो देखते हैं कि वर्टिकल मोमेंटम इक्वेशन in the vertical momentum equation how we can apply the scale analysis okay. चलो तो dw dt is equal to minus 1 by rho delta p delta z minus g and along with that you can have 2 omega u cos phi okay this is your general yeah, Fourier force for the z direction. Vertical momentum equation. So z direction. Okay, so let us write dwdt as the local term as we have written in the horizontal one. So local term plus advective term. So u delta w by delta x plus v delta w by delta y plus w delta w by delta z. And the right hand side terms are as it is minus g plus 2 omega u cos phi. Perfect. This is okay. Now, What should we do here is that, so delta W delta T. How can we write this as the scale analysis part? So delta W is W, T is, you can write L by U. We have seen this. U delta W delta X, U is the horizontal wind, W is the vertical wind, and X is the horizontal length scale. V delta same, U W by L. This is W into W divided by H. Remember, this delta Z. This is, remember, this is your delta P of Z. Rho is 1, you can keep it like this, and delta Z is H. This is G, and what about this? See, 2 omega sine phi. So mid latitude synoptic system, we generally assume phi to be 45. Is an assumption. You can make it 35. Right? So just keep it easiest one. So at phi is equal to 45, you have 2 omega sine phi and 2 omega cos phi are same, which is nothing but the S, which is nothing but 10 to the power minus 4 per second. And you have a U with this. So what you get finally is your F times U. Okay, because there is a U here. So these are the scaled version. Now we will put the values and try to see. W is 10 to the power minus 2. U is 10 divided by 10 to the power 6. Same, 10 to the power minus 2, 10 divided by 10 to the power 6. 10 to the power minus 2 into 10 divided by 10 to the power 6. W square, 10 to the power minus 2 whole square divided by 10 to the power 4. On the right hand side, remember, this is delta P Z. So it is 10 to the power 5 pascals divided by rho is 1. This is 10 to the power 4. This is 10. What about this? 10 to the power minus 4 into 10. These are the scales. Fine. So this will be 10 to the power minus 1. Okay. So what will this give? 10 to the power minus 7. Right? Yes. Right. This is also 10 to the power minus 7. This is also 10 to the power minus 7. This part, this part. What about this? 10 to the power minus 4, 10 to the power minus 8, even lower than this, equals, come back here, this gives you 10, this will give you 10, and this will give you 10 to the power minus 3. So, on the, again, on the left hand side, so LHS scales are very, very small. Scales are very small. So, your dWdt can be ignored, right? All these local term plus adjective term, they can all be ignored because you have the dominant values 10. Even the Coriolis force, the vertical Coriolis force, that is also small, 10 to the power minus 3. So the dominant terms will be the pressure and radial force 1 by rho delta Q delta Z with a minus sign and minus G, which is equal to 0. This is the dominant balance. And this balance delta P delta Z is equal to minus rho times G, or because pressure is depending on Z only, so dP dZ is equal to minus rho times G. This, what it is, what is called as the hydrostatic balance. So in the mid-latitude synoptic system, hydrostatic balance is very common. But when you have convection, like in the tropics, okay, every day you see that there are convective features. Cloud starts growing from uh, afternoon towards the evening time. That is your convective. So there you cannot use this balance. There you will have this vertical velocity. This dWdt will be no longer negligible. Okay. So for that, this is the hydrostatic balance will not be applied in the tropics in a particular time. But in mid latitude, you can have this hydrostatic balance. Okay. So I have told you that while solving the assignment question, one of the questions were there that in the vertical momentum equation, which of the terms are dominant? So these are the dominant terms, the pressure gradient and the gravity. So there was another option, which is the Coriolis. You can see that the Coriolis term is also very small. Okay, so it is negligible. Fine. So what he notes, what we get from the scale analysis of horizontal momentum equation and vertical momentum equation, that if you apply the scale analysis based on the mid latitude synoptic scale, then you will get a diagnostic balance which you cannot predict, but a balance can be established, which is the geostrophic balance. But for the vertical momentum equation, you get another balance, which is also a diagnostic balance, which is the hydrostatic equation or hydrostatic balance. Okay, so these are the two things which we have discovered. Okay, fine. Now we can apply it to many other things. That is, we can apply it to mass conservation equation, like the continuity equation, and we will apply it to thermodynamic energy equation. Okay, which we have derived in the last class. So what we will do is that once when we are doing this mass conservation, we are applying the scale analysis, we will use a method. Okay, later we will term that as the perturbation method in the wave theory. So we will see that today. Okay, so just give me a moment. I will start the scale analysis part of the continuum. Okay, so now we will apply the third part is that about the continuity equation. Continuity equation we have derived. We all know what is the continuity equation is the mass conservation. That's all. Okay. So what was the equation? 1 by rho d rho dt, where rho is the density, plus del dot u, the divergence of velocity, is equal to 0. This u consists of u, v, and w. Is a vector. Okay. Now, what we will do here is that let's see this. See this d rho dt. Can we write this equation d rho dt plus rho del dot u is equal to 0? D rho dt can be written as the local term, the delta rho delta t, plus the advective term, that is u dot grad rho plus rho del dot u is equal to 0. This is the basic uh, theorems, not theorems, the equations. Okay. Now, delta rho delta t plus what else we can do? What we do is that, uh, okay, fine, let us stop it here. Okay, this is the final form of the continuity equation which we have here. Now we will apply a method, that is this rho, the density, is written as a rho naught, which is only a function of z, only varying in the height scale, not in the uh, horizontal scale. Okay, plus the rho dash, the perturbation x, y, z, and also t. Fine. And we say that this rho dash by rho naught is much, much less than 1. So what is essentially happening is that, so you have your mean state. Okay, this is your suppose the mean state. And there are some little bit of perturbations. Okay. These perturbations are rho dash, but this mean state is rho naught. Okay. Together with this, you will get something like this. Okay. So mean plus the perturbation. This is the actual rho. Okay, so we can always write it like this. And we are assuming that this rho naught in time x and y is almost negligible. The variations are negligible. So we are only considering the mean states only in the z direction. Fine. Now let us apply these perturbations in this equation. All right, so let's do that. So what we will have, delta rho dash by delta t plus u dot grad rho dash plus w into e rho naught by dz plus rho naught del dot u is equal to 0. Okay, have you understand this? Let's see. Let me write it here. See, you have del t term, right? So what I have done is that rho naught plus rho dash, and then what? Then you have u dot grad rho dash. Okay, so okay, plus w delta rho by delta z. So this is rho naught plus rho dash. Everywhere it is rho naught plus rho dash. Okay, let me rub this one and derive it properly. Okay, this is okay plus rho naught plus rho dash del dot u is equal to 0. Everywhere I have written rho as rho naught plus rho dash. Tell me, this rho naught, is it a function of time? No, we have not considered. We have said that it is 0. So rho dash is, so delta rho dash by delta t. If you differentiate a constant, it will be 0 plus. Okay, now this u which we are writing here is consisting of u and v. Okay, and this is w. So just writing it in a different way. Okay, so u delta rho naught plus rho dash delta x plus v delta rho naught plus rho dash by delta y plus w delta delta z of rho naught plus rho dash plus rho naught plus rho dash del dot u. This is what your equation is. Correct? Now, first term we have already seen. What about the second term? Is rho naught a function of x? No. So u delta rho dash by delta plus v. Is rho naught a function of y? No. So delta rho dash by delta y plus w. Is rho naught a function of z? Yes. And is rho dash a function of z? Yes. But rho naught, as we have assumed, is much greater than rho dash. Therefore, we will consider only the rho naught part. So it will be delta rho naught by delta z plus, what about here? Rho naught is much greater than rho dash. So you can put rho naught del dot u. That's all. That is equal to 0. Okay. Now see, this rho naught only is a only function of z. So delta z of rho naught z, it can be written as d rho naught by dz. We can write. So delta rho dash by delta t. Finally, u delta rho dash by delta x plus b delta rho dash by delta y plus w d rho naught by dz plus rho naught del dot u is equal to 0. Now this is clear how it is coming. So this is how the perturbation thing is being applied. Also, for the synaptic tail motion, it is observed that rho dash by this rho naught is roughly about around 10 to the power minus 2. Okay, this is an observed quantity, just like the scales which we have observed. Now what I will do is that I will divide this rho naught throughout and say that this is 1 by rho naught delta rho dash by delta t plus, okay, so u delta rho dash by delta x plus v delta rho dash by delta y plus finally w d rho naught by dz is equal to uh, or plus rho naught del dot u. So rho naught is not here now because I have divided it. So this by rho naught. Fine. Okay. Let's see the first term, the entire bracketed term. Let's see what is its scale. 1 by rho naught delta rho dash by delta t plus u delta rho dash by delta x plus v delta rho dash by delta y. Okay, so what is there? So this is rho dash everywhere. It is rho dash divided by there is a rho naught and there is also a u by L. See, for this, it will be rho dash by rho naught by t. T can be written as u by L, just like the other one. So, finally, this case will be this, and which is equal to 10 to the power minus 2 into 10 divided by 10 to the power 6. So, gives you 10 to the power minus 7. Okay, so the first bracketed term is having scale value 10 to the power minus 7. Let's say this, that is w by rho naught d rho naught by dz. Okay, so this is nothing but w by h because rho naught cancels. So this gives you 10 to the power minus 2 divided by 10 to the power 4, which is 10 to the power minus 6. And we have the third term, del dot u, which is what this is what delta u delta x plus delta v delta y plus delta w delta z. Apply it. So it will be 10 divided by 10 to the power 6. This is also same. And this will be 10 to the power minus 2 divided by 10 to the power 4. So this is what 10 to the power minus 2. Sorry, minus 5. So this is 10 to the power minus 6. So this is the largest part. So 10 to the power minus 5. This is 10 to the power minus 6. So only del dot u equal to 0 cannot come. So I will also see this and this. I will not take 10 to the power minus 7. So finally, my equation will be 1 by rho naught w d rho naught by dz plus del dot u equals 0. Okay. Although I am getting the horizontal velocity divergence is 0 because 10 to the power minus 5, this is the dominant term, these two. But still, if you have to take the vertical velocity, you can take. Okay, for this case. All right. So this is one of the things. Okay, and we have applied here the perturbation method, and we will see in the wave theory also the perturbation method. Okay, so I am just thinking whether I will do the thermodynamic energy equation uh, thing, or otherwise we can shift it to the wave theory. Okay, because that is also important. So let's go to the waves, because this thermodynamic energy equation also can be derived in the same way. The scale analysis can be applied, and it is already, I think, given in the lecture notes. So let's stop that and let's start the. Ha. Hmm. Ha. Ha. Yes. No, 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 no. Time. T, T, T. T x y tends to. Ha. Uh, मैं यही बोलना चाह रहा था कि जो रो नॉट है उसका वेरिएशन एक्स वाई और टाइम पे नहीं है इस सिर्फ जेड में है। हाँ, तो मेरा मतलब ये था कि रो इज इक्वल टू ओनली रो नॉट ऑफ जेड, इट्स नॉट यही यही बोल रहा हूँ। ओके, so let's start the waves. So in physics we all know different definitions of it. So I will write a couple of things and then I will show one animation I have found out about the group velocity and phase velocity. We all know this, but animation makes it much more better. Okay, so waves. First of all, before going to waves, we should know what is means oscillations and how the waves travel. All these things will be there. Okay, so the basic definition of waves will be like this. So it can be called as some kind of a perturbation, some kind of a disturbance. So the disturbance or disturbances that transfer energy and momentum actually, both momentum and energy from one point to another. But very important thing which you have to be careful while defining without the transfer of medium particles. Medium particles will remain wherever it is. It will oscillate, but the wave will propagate. So how it is like? So I'll show you. Animation thing will be much more clearer, but let me try to show this. So this is at some instant in a 1D kind of a thing, or not 1D, it's a 2D kind of a thing. Okay, this is the material medium where particles are there. Okay, so this particle is here, one particle is here, second particle is here, third particle is somewhere here, fourth particle is here, like this. Okay, so like this, it is. This is the one screenshot I would say. At one instant, instantaneous shot. If you take a picture, this is how it looks like. Okay, this is at some instant t is equal to t1, let's say. Okay, so you can make this. This looks like so. What is happening is that each particle here is oscillating in the say y direction. This is suppose x, this is in the y. In the y direction, the particles are oscillating. But remember, these particles are not moving in the x direction. This is to be very clearly, one must be clear about it. Okay. Now what happens in the next instant is that you have the same material medium, but this particle which is here is now it has come down from here. This has come here somewhat little. This has come here. This is somewhat little down. This, and like that. Okay, so let me. It's difficult to make. Okay, so each particle I am not making it properly, but this is something like this. So the wave now comes here, somewhere. Yeah, comes like this. So here, suppose this is the maximum amplitude. The same particle now is here. It has reduced a bit. Now the maximum is happening here. So you can see that although the same particle is present here, but its oscillation amplitude changes, and hence the wave propagates in the positive x direction. So this is some e is equal to t2. So now this is the maximum amplitude, but earlier case it was not the maximum amplitude. So it has traveled this. The wave has traveled in the x-axis, but the particle has not traveled. Particle is oscillating in the y direction. This is the basic thing about the waves. A disturbance is propagating in the positive x direction. However, the material medium particles remains as it is there, but oscillating. That's all. This is the wave. Okay, so I would say the wave is moving in x direction. Okay, and there are some different definitions. For example, let's say amplitude. We define amplitude of oscillation also, but amplitude is actually what I have seen in the definition, half distance. Actually, not the distance, I would say half height. Okay, half height between crest and trough. Now, question is that what is crest and what is trough? So this the maximum is crest, the minimum is trough. Okay. So half height between the maximum and the minimum. So if you have this, okay, so this is the height of the crest and this is the height of the trough. So half height, this is the amplitude. Okay, this is one of the definitions. Number two is the wavelength. So wavelength is the distance. So these are all known things. Distance between two consecutive crests and troughs. Okay, so two consecutive crests or two consecutive troughs. Sorry, this definition is not true. Two consecutive crests or two consecutive troughs. So make a large number of crests and troughs. So this is a crest, this is another crest. This two consecutive crests, the distance between that is your lambda, which is the wavelength. Or you take the troughs, this is your lambda. So this is the one wavelength. So next is wave number. This is important for particularly for the wave directions and all. This comes out to be a vector. Okay. So how will we define this? Generally, it is defined as nu as 1 by lambda. So what is the physical meaning of that? Is that number of waves, number of waves in unit length or unit distance. Okay, number of waves, or you can write the number of wavelength. So this is one wavelength. One wavelength in unit distance is your nu. So if you have a unit distance like this is one unit, and you have this. So how many waves are there? This is one wavelength can be covered. This is the second wavelength, so almost two. Okay, so it has its wave number becomes two. There is another thing which is called the angular wave number, just nothing but multiplied by 2 pi radians. That's all. This is your angular wave number. Same definition, but in it, instead of one unit distance, it is saying that in a 2 pi radians of the circle, how much is the number of waves? Angular wave number. Okay. Next, we define a wave vector. For that, we write A is the wave number. K is the wave number uh, in x direction, suppose. So you can understand that in the atmosphere there are three dimensions: zonal, meridional, and the z directions. So corresponding to that, the wave number in y direction is L, and M is the wave number in z direction. So this is the typical signs and symbols which we follow. So how it will be defined? So k will be equal to 2 pi by lambda x, the x wavelength. L is 2 pi by lambda y wavelength, and m is 2 pi by lambda z. This is the wave number. Now, the wave vector, wave propagation vector can be written as k I hat L j hat m k hat. Okay, this is your propagation vector or angular wave number vector, whatever you want to say. What will be its magnitude? Simple. It is just the square root of a square plus a square plus a. All right. So this is all about the wave number. Next is the angular frequency. This is the third one. Fourth. Fourth is the angular frequency. So simple. What is frequency by the way? Frequency is f is equal to 1 by t, the time period. Okay. So per unit time. So unit is in hertz, the SI unit. So it is nothing but number of oscillations per unit time. That is your frequency. And for the angular case, you just have omega, which is 2 pi by. This we have always used, many times we have used, particularly for geostationary satellites and all those things, we have used this. Okay, so that's all. Now, you will have, definitely you will have a wave equation, which will be three dimensions, so 3D wave equation. We are not going into details of the wave equation, you can look into it, but we are mostly interested in the solution of the wave equation. And one such beautiful solution of wave equation is something like this. A cosine or sine, whatever you wanted to take, kx minus omega t. Actually, for 3D, it can be written as A cos the k vector dot x vector minus omega t, where k vector is nothing but ki plus lj plus lk, and x vector is x of xi plus yj plus zk. So x, y, z are the displacements in the x, y, and z direction. Okay, this is simple. Now, so let's follow the 1D. This is 1D, this is 3D. So for 1D, let us see. So A cos kx minus omega t, right? So A is, it's the amplitude of the wave, and whatever the cosine part is there, this is called the phase. Okay, is the phase of the wave. Okay. Now, from here, we can try to see the phase velocity. So this phase is denoted as phi. So a wave, just like which I have shown here, this wave, this can be considered as one of the phase. And it seems like this phase, this phi, is moving here like this. But it will be the same constant phase, remember. The phase will be same. So what is happening is that what I will see is that, so this is what I'm trying to make, is that you have a wave like this, and the next instant of time, this has shifted this. Okay, so this, suppose this is one of the phase angle, and this is another phase, but this phase and this phase are same. This is the phi, this is the same phi, but it has traveled in the x direction. Okay, what I will do is that I will make the d phi dt is equal to 0. With time, the phase is not changing. See, it is remaining the phi, the same region or the same part of the wave, which is pi. This is same equal to 0. But wave is propagating. So we will see that what velocity it will propagate. So what is phi? We have already seen that kx minus omega t is phi. Let's differentiate with respect to time. So what you get? K dx by dt minus omega. This is 0 because the phase is not changing. But phases, what I mean to say is that this see, this is the amplitude, right? This part is not changing. This is the maximum part. This is also the maximum part. So it is not changing with time, but the phase, the pi, this pi part, is propagating in the x direction with time. So that change in delta x in change in delta t is what we are focused in. So this becomes k, and this we call as the phase velocity. Change in delta x by change in delta time minus omega. So c, the phase velocity is nothing but omega by k. Okay, so this is called the phase velocity. Actually, this is not the phase velocity, but it is the phase speed because there is no uh, vector associated with it here. This is phase speed. Okay. But in 3D, there are different types omega by k, omega by l, omega by j. But still, it will be called as the phase speed. Okay. This is omega by k. Now, what we will do is that this is for one wave. Now, when there are two waves and they're interacting with each other, we get the superposition of a linear superposition of waves. There, along with this phase velocity or phase speed, there is another velocity which is called the group velocity will come. Okay, so we will derive that and try to see. Okay, so the fifth one is the group velocity. And once we see this, we will then go to the animation part. It's a simple visualization. Okay, so what I'm trying to make here is that when you have more than one wave, more than one wave interacting. Okay, so one wave is here. Let us say this is this particular wave. Another wave is somewhere here. Okay, and they are superimposing each other. Final wave will look something like this. Okay, so it's a superposition kind of thing. Or the better example is this. So suppose you have a wave which is like this. Okay, and you have some small waves also with this. Okay, so it's like okay, so you can see that the packet of waves are moving. So this is the group velocity. I'll show the derivation that will be easy, and then the animation will make it much more clear. So let us consider y is equal to some y1 plus y2, the linear superimposition. First wave y1 is having a e to the power iota. Things which are changing is the wave vector, that is k, the angular wave number. In one case, it is k plus delta k into x minus omega plus delta omega into t. Okay, why? Okay, e to the power iota. So you know that sine, cos can be together made as e to the power iota. You know this thing is known, right? So it can be written like you can try with sine, you can try with cos. Results will not change. Y2, same amplitude I am keeping for my simplicity, iota, and in here we get k minus delta k. So in one case it is k plus delta k, omega plus delta omega. Here it is all in minus. The change is in minus. Fine. So these are the two waves. Let's have y is equal to y1 plus y2, linear superimposition, and sorry, linear superposition, not superimposition, but position. So this becomes a can be taken common e to the power. Let's write it very carefully, otherwise it will be sometimes problematic. So iota, uh, so this is kx minus omega t plus delta kx minus delta omega t. All right, e to the power iota kx minus omega t minus delta kx plus delta omega t. All right, this is fine. Now, out of which can we take something common? See this kx minus omega t, kx minus omega t, e to the power. So, can we write a e to the power iota kx minus omega t can be taken common, and you have e to the power iota delta kx minus delta omega t plus e to the power. Can we take a minus iota and you have delta kx minus delta omega t. So what you get finally is y a e to the power iota kx minus omega t, and at the same time you have e to the power iota kx minus, oh sorry, so e to the power iota delta kx minus delta omega t plus e to the power minus iota delta kx minus delta omega t. Now, if I divide by 2 and multiply by 2, what you get? So it will be 2a e to the power iota kx minus omega t. Can we write this as cosine of delta kx minus delta omega t? That's all. This is what we have. So this will be this 2a times this becomes the amplitude of the group wave, the packet of the wave, and this is your the normal wave potential. So this part will give you the phase speed which we have derived, and this part will give you the group velocity. So again, the same thing. This is the phi g, the phase of the group. So we will say that the d phi g by dt. See, the phase is not changing with time, but your phase is not changing with time, but your wave, the group of waves are propagating. So put that equal to 0, and you will get an expression of Cg as delta omega by delta t. The change in omega to that of the change in the wave length. This is your group velocity. Okay, and this can be written as delta omega by delta k I hat plus delta omega by delta L j hat and delta omega by delta M k hat. So this is the group velocity. Okay, so this is what you have. Along with this group velocity and phase velocity, you have certain other things which are the dispersive waves. Dispersive waves. Dispersive waves. There is a criterion where you have a, I would say, relation between omega and k. So wave vector and your angular frequency must have a relation, or is a, or I would say omega must be a function of k. Okay, or you can say that c must be proportional to k, or proportional, or I would say it's a function of k. Okay, this is one of the things. Also, the group velocity must not be equal to the phase velocity. Then only it is the dispersive phase. So these are a couple of criteria. Second is non-dispersive. So dispersive waves, like you have internal gravity waves, you will see that in this internal gravity waves, if it is being covered, I am not sure whether it is covered or not. So your omega is something of the order like this, k upon root over k square plus a square plus a square. Okay, something, some expressions are there, but look at this. Omega is a function of k, the wave vector. Okay, so this is important. So omega must actually omega must be the function of k. Then comes the C, where omega by k is there. Okay. So non-dispersive waves, where Cg, the group velocity, will be equal to the phase velocity, number one, and shape of wave packet. Because of this expression, shape of wave packet does not change with time. And one of the typical example of this is the acoustic wave or the sound wave. Where is it important? Uh, when there is a lightning, there is a thunder in case of a thunderstorm. Because of the temperature change, sudden temperature change, and there is a strong temperature change, a wave propagates. That is called the acoustic waves or the sound waves. Okay, so for this sound waves, you don't find this. There is a dispersion. Okay, because your uh, c, the phase velocity, is is actually equal to something like this, gamma or t rho. So it does not consist of k, the wave vector. So c is not a function of k. Okay, so this is the acoustic waves. Is one of the examples of non-dispersive waves. Okay, so let's now see the quickly see the animation of a couple of things. You can also visit this website. I found this advertisement. Okay, see, this is one of the things. I have taken two packets. Means these two things you can see. Okay, and let me play first. Phase velocity equal to group velocity, kind of a non-dispersive nature. So the yellow dot and the red dot are all in the same direction or at the same place. It's not changing. So and the wave packets you can see is not changing with time. It's there. Okay. Now, how will you understand that wave packets are changing with time? When you make phase velocity say greater than group velocity. See, now the wave packets are changing with time. You can clearly see it. Okay. And this yellow dot is your group velocity, and the red dot is your phase velocity. Okay. So you can see it here very clearly, right? So this is how it is shown. Next, you can see many things. The phase velocity is less than group velocity. So you can see the yellow dot is traveling much faster than the red dot, which is the phase velocity. And what I'm trying to tell you is that, see, this red part, it's not changing. It's the point is not changing. So that's why we have made this phi constant with time. Okay. So this is how you can just check. I think this is just if you type in Google that animation of group and phase velocity, you will see this one of the websites. Just check, play around with different web packets and different conditions. Okay, so this is what I wanted. So these are all dispersive waves. All dispersive waves. Only non-dispersive waves comes when it is here. Nothing is changing. Everything is in the packets, but not changing. Fine. Let's come to our part. Okay. Now we will go to the perturbation method and may not solve it completely, but let's see. Just give some hint. Maybe we can continue in the next session. Okay. But before that, let me star mark some important balances because I can see some in assignment 4 there are some balances noted. So important balances. Let me. Of course, these balances you can find in the internet, in the Google. Fine. So first is what we have discussed today. That is the geostrophic. The geostrophic balance. This is the balance between the pressure gradient force and the Coriolis force. This is we have seen. Second is the gradient wind balance. gradient wind balance. Okay, which is between the pressure gradient, Coriolis, and the third is the centrifugal. Centrifugal is must for the gradient wind balance. Third, cyclostrophic balance. Cyclostrophic balance. This is this can be applied in case of the cyclones when it is near the equator. Near the equator, Coriolis force is zero. So pressure gradient should balance the centrifugal. Coriolis is neglected. Coriolis force neglected. If you carefully watch the cyclone formation, it starts from the equator, near the equator, and in near the equator, it follows the cyclostrophic balance, and then when it goes towards to the north, you will find the Coriolis force starts acting. Okay. So this is one of the things. Fourth is inertial waves. So as the name suggests, it's only dependent on the what you call the pseudo forces. So centrifugal is the balance between centrifugal and Coriolis. Okay, so these are the couple of balances. There are other balances like the thermal wind balance, which depends on the temperature gradient. Okay, so these are the couple of balances which I thought that might be important. So just mention it. Okay, now is that why we require this wave theory in our atmospheric field. Okay. So if you list down all the equations which we have studied, you will find that, say, suppose the x momentum equation. How we write? We write delta u delta t plus u delta u delta x plus v delta u delta y plus w delta u delta z, right, is equal to minus 1 by rho delta p delta x plus f d. Right? This is what the general momentum equation. Look at these terms. V delta U delta Y, W delta U delta Z, U delta U delta Z. These are all non-linear terms. Why non-linear terms? Because it's there is a product of the differentiation and the actual variable. So these are all non-linear terms. And non-linear terms are very difficult to solve analytically. It's very difficult to solve analytically. But we need this equation to be solved to have an idea or to give the forecast of the weather, right? So for that, how to solve it? There are two methods. For the nonlinear differential, partial differential equations, we have two methods to solve. One is the numerical method. Okay, one is the numerical method, which consists of the finite difference method, forward iteration, backward iteration, all those things. And the second is your wave perturbation method. This is another. And if you are familiar with the weather models or the your global circulation model, general circulation models, GCMs, which we call, they either consist of this numerical or this wave perturbation method. The wave perturbation based models are called a spectral model, and numerical methods are called the grid based model. Grid based numerical model. Okay. One of the example of grid-based numerical model is your income. NCMRWF uses it. So yeah, NCMRWF, National Center for medium range weather forecasting. It is in Noida, Delhi, India, and the spectral model is used by the Indian Meteorological Department, IMD, GFS. And recently there is a recent advancement of our forecasting system, which is the Bharat forecasting system, the BFS, the Bharat forecasting system. Recently, the weather updates are being given by using this model. Okay, so all these are the spectral model based on these wave perturbation techniques. And there are other things, spherical harmonics are there, and other things are there. There are too many complications. We will not go into that detail. We will just focus on how wave perturbation method can solve our equations or yeah, wave equations. Okay, so the perturbation method, this things that uh, u, any field, say u, can be written as u mean state and u dash. Generally, this is called as the mean state or base state, and this u dash is the perturbation. Okay, so that the thing which I was talking, that this is your u velocity, suppose at different times. Now there is a, what we can say is that there is a mean value of this, and there are some perturbations over this, which will give you this. Okay, this is what it means. All right. Now what we will do is that the perturbation method, particularly perturbation method, has two things. One is perturbation or perturbations are always less than the mean state or the base state. And not only less, these are much less. Okay. The second one is both perturbation and base state term, base state components should satisfy the governing equation. Satisfy governing equation. Third is that product of perturbation terms are neglected. So if let me so if while putting this thing in the equation, if you get a term u dash into u dash, this can be neglected or into zero. This will be zero. Okay. Now what we generally assume is that your u bar is nothing but a function of, or we generally consider this is a constant state. It's nothing a function of not even in x, y, z or t. Okay, it's a constant state. But for the time being, we can write that it is varying only in space, not in time. So time being, let us consider for the time being. Okay, and the perturbation state u dash will be function of everything. Time, x, y, z. It will be always like this. But here we can put some assumptions. Okay. We will see in the next session when it starts. We will try to reproduce the momentum equation by this perturbation method and try to see what we get. Okay. And then we can proceed after that. Okay. So here I think I can stop today because there is a large derivation after this. So better to stop here. And if you have any questions, sure. Hmm, 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 hmm. हम्म 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 राइट राइट हम्म हम्म तो मैं इसका आंसर ऐसे दूंगा कि जो डीप ब्रॉगली ने किया था, डीप ब्रॉय वेवलेंथ वगैरह सब कुछ है, बट दैट इज द स्टार्टिंग पॉइंट ऑफ द क्वांटम मैकेनिक्स, राइट? और यहाँ पे जो स्केल है दैट इज मच लार्जर देन दैट। तो जब इतने लार्ज स्केल में हम लोग, मैं ये बोल डेफिनेटली बोलूंगा कि क्वांटम स्टेट्स आर स्टिल वैलिड इन द लार्ज क्लासिकल मैकेनिक्स, बट ये क्वांटम स्टेट्स के बीच में जो अगर तुम एनर्जी स्टेट्स देखोगे, देयर इज अ वेरी लिटिल गैप। जो एनर्जी स्टेट्स हम लोग क्वांटम में बनाते हैं फिजिक्स में जनरली, देयर इज अ वेरी लिटिल गैप। तो उसका कोई महत्व यहाँ नहीं है। बट एज यू गो इनटू द माइन्यूट स्केल्स, डीप जाओगे थोड़ा, वेव लेंथ जो है, सॉरी नॉट वेव लेंथ, जो पार्टिकल साइज है वो अगर जब बहुत छोटा होता जाएगा, एंगस्ट्रॉम यूनिट्स में होता जाएगा, डियर इट विल वर्क। आपको अगर याद होगा तो डी वेवलेंथ ये सब एंगस्ट्रॉम यूनिट्स में होता है, बहुत छोटा छोटा। हाँ? तो यहाँ पे वो चीज वैलिड नहीं है, यहाँ पे मोर ऑफ ए न्यूटोनियन मैकेनिक्स वैलिड है। नहीं, कुछ वेव्स डिस्पर्सिव होते हैं। जैसे मैंने बताया इंटरनल ग्रेविटी वेव्स, हम लोग आगे देखेंगे। जब वेव्स के मतलब डिफरेंट वेव सॉल्यूशंस हम लोग डिराइव करेंगे, तो देखना हम लोग को मिलेगा कि जो अपना फेज वेलोसिटी है दैट इज डिपेंडिंग ऑन दोज थिंग्स लाइक द वेव वेक्टर्स, वेव प्रोपगेशन वेक्टर। तो ऐसा हम लोग कह नहीं सकते कि इससे कंप्लीटली नॉन डिस्पर्सिव मीडियम, बट होता है उसमें भी ये ट्रेवल करते हैं, और हम लोग आगे देखेंगे। अगर इस कोर्स में है, आई एम नॉट वेरी श्योर, मैं देखूंगा एक बार। ठीक है, ओके ओके, चलो प्लीज स्टॉप।